So, in the last lecture I covered case 1 of the analysis, right, for the stability analysis of the maximum Hebbian based maximum eigenfilter. So, what we looked into was the case where we consider all the modes except the principal mode, that is for 1 less than k less than or equal to m, that was the case that we considered, and showed that all these modes dive to 0 asymptotically. So, that leaves us with a question, what happens to the principal mode, and then we have to analyze that case. Okay. So, let us consider the case where k equal to 1. So, my governing differential equation is d theta 1 of t upon dt is equal to lambda 1 times theta 1 of t minus theta 1 of t times this summation having all the components, eigen components, L equals 1 to m lambda L theta L square of t. So, it is a function of the lambda I theta I equals 1 to m. Okay. Now, we simplify this equation to be lambda 1 theta 1 of t minus, so I pull this L equals 1 case, and the L equals 1 case is corresponding to theta 1. So, it is going to be lambda times theta 1. So, it is a lambda 1 here, right, lambda 1 times you have a theta 1 here and we have a theta 1 square of t sticking out. So, we have lambda 1 theta 1 cube of t minus theta 1 of t summation over all L not equal to 1, right, it is L equals 2 to m, we have the summation. But here is an important detail. From case 1 of our analysis that we just did earlier, alpha L for L not equal to 1 as t goes to infinity dives to 0. So, you have all these theta L square of t, these terms for L not equal to 1 they go to 0. So, let us see this what really happens. So, basically you have a governing equation which is d theta 1 of t by dt is lambda 1 theta 1 of t times 1 minus theta 1 square of t. Why? Because all these dive to 0. I will just put this in red. Okay. So, asymptotically what we have is this equation which is d theta 1 by dt is lambda 1 theta 1 of t times 1 minus theta 1 square of t. Now, like what we did earlier, we need to analyze the stability of the system, for which we require Lyapunov functions, because when we look into stability of linear dynamical systems, we can basically look at the homogeneous equation and then look at the roots of this homogeneous equation, and then from there we can make our analysis whether it is stable, unstable, or it is oscillatory. But this is a nonlinear system. The analysis or the stability analysis of nonlinear systems is not straightforward, for which you require something called Lyapunov functions. So, I will just briefly use a particular Lyapunov function for this analysis and touching upon some details on Lyapunov functions, but a formal treatment of Lyapunov functions is part of a nonlinear dynamics course. So, that is a separate course, separate graduate level course. Okay. So, we need a Lyapunov function, and that is a positive definite function. Now, let us start with some basics of these nonlinear dynamic systems related to this topic of Lyapunov and the functional form that we need for this particular example. Let S be the state vector of an autonomous system, it is a nonlinear autonomous system. Let V of t be the Lyapunov function of the system. An equilibrium state denoted by S EQ in the superscript of the system is automatically stable if it satisfies this condition that dV by dt is less than 0 for all points or all vectors S belonging to u minus S, that is, this u is a small neighborhood around S, and you remove this equilibrium point around this. For all these points in u minus this equilibrium point, this derivative of this the derivative of the Lyapunov function is negative. Now the question again is how to get this Lyapunov function, and that seems more like an art than precisely saying that you can have a Lyapunov function that satisfies generically or generally for these nonlinear functions. So we do not have such a kind of theory here. So you have to bring in, so if you can show the existence of a Lyapunov function and then proceed with the analysis, then we can guarantee the stability of the nonlinear system. Okay, so let us get into the details. So for our problem at hand, which is basically the analysis of the Hebbian based maximum eigenfilter, the differential equation has a Lyapunov function given by this quantity, which is v of t is theta 1 square of t minus 1 whole square. Of course you would be questioning at this point, how did I get this form for the Lyapunov function? As I told you earlier, the choice of the Lyapunov function depends upon the nonlinear system at hand. There is no one Lyapunov function which generically works for all nonlinear systems, and that's how it nonlinear dynamics, stability analysis of nonlinear systems work. So we assume this form based upon intuition, and then we validate this assertion if it satisfies certain properties. Now the first condition is dV upon dt, dV of t upon dt is less than 0 for all t, and v of t has a minimum, right. We need to validate these assertions. So let us compute the derivative. So if you recall, v of t is basically theta 1 square of t minus 1 whole square. So this is equation 8. So when I take the derivative, just I apply chain rule here, I get 4 times theta 1 of t times theta square of t minus 1 times d theta 1 upon dt, right. Theta 1 is a function of time. So I just this is x square, I get 2x, where x is theta 1 square t minus 1, and I have to take the derivative with respect to this x, which is again 2 theta 1 times d theta 1 of t by dt. That is what I get. So now once I do this, I get dV by dt, but I need what d theta 1 of t upon dt is. I need this equation. So we have done this earlier. So d theta 1 of t by dt is given by lambda 1 theta 1 of t minus theta 1 of t times this summation from L equals 1 to m lambda L theta L square of t. But from our previous analysis, right, all these theta L's dive to 0 except theta 1. So we retain theta 1 and let everything go to 0. So when we do the simplification, so we have the second term has theta 1 t which is sticking out, and then you have lambda 1 and theta 1 square t corresponding to the term L equal to 1. So what we get is we get lambda 1 theta 1 t minus lambda 1 theta 1 of t times theta 1 square of t, and you simplify all this, you get this final equation which is minus lambda 1 theta 1 of t times theta 1 square of t minus 1. That is equation 9b in my terminology here. So, you plug in 9b into 9a and then you simplify this further, right. When we do this, we get dv by dt is given by this quantity here, which is minus 4 times lambda 1 theta 1 square of t times this quantity theta 1 square of t minus 1 whole square. Now, our data correlation matrix R has positive definite property, which means the eigenvalue, I mean eigenvalue lambda 1, because lambda 1 is interesting to us here. We do not care about the other eigen components, because all those principal modes except the first mode dives to 0, right. So, the eigenvalue lambda 1 is positive. Therefore, dv by dt is less than 0, right. So, we can so you look at this equation here dv by dt. So, you have a minus sign sticking over, and all these are square quantities. I mean square theta 1 square is positive, theta 1 square minus 1 the whole square is also positive. The only thing that is a detail is lambda 1, but because of positive definite property lambda 1 is greater than 0. So, all the quantities here are all having positive sign except this negative sign which is sticking out here. So, therefore, dv by dt is less than 0. Okay. Now, v of t has minimum at theta 1 of t being plus minus 1, right. It is like a quadratic bowl here, and right this is trivially the saddle points are theta 1 equal to 0 and then theta 1 equals plus minus 1, and we are interested in the case when theta 1 is plus minus 1, the 0 case we ignore, and this is a non trivial case. And the second condition is also satisfied, that v of t has a minimum. So, now what it means is theta 1 of t as t goes to infinity heads to plus minus 1, and all your other modes theta k of t as t goes to infinity they dive to 0. Okay. So, this is a useful thing for us, because we say that the first component remains, and then this theta 1 of t can go to plus 1 or minus 1, right. And what it really means is the maximum Hebbian based maximum eigen filter extracts the first principal component. So, if you look at this data correlation matrix and get your eigenvalues and eigenvectors, this algorithm, which is the Oyer's rule, which is basically the normalized Hebbian update, extracts the first principal component adaptively. So, what it means is, if you consider this complicated stochastic differential equation in vector form that we wrote, right. We started off with this equation. Now, you get this function theta 1 of t and all other modes dive to 0, and then theta 1 of t will converge to plus minus 1, and as a consequence what it really means is this weight vector w of t, this is very important, the weight vector asymptotically converges to q1, where q1 is the normalized eigenvector associated with the largest eigenvalue lambda 1 of the correlation matrix R. Now, if you were to pause here and then ponder what is happening, so all that was done in the Hebbian update was you were trying to take a projection, you were taking this weight update at time n plus 1, which is weight update at time n, plus some eta times the output times the input. Input is a vector which is the presynaptic input, and w of n sorry the y of n, which is the output, was a scalar, and it was the post synaptic output, right. So, this simple update upon normalization, the weight vector converges to the normalized eigenvector associated with the largest eigenvalue within the data correlation matrix. Now, from condition 6 of the asymptotic stability theorem, I mean we discussed various conditions. So, if you recall, so there exists a subset A of the set of vectors such that this limit in the limit the limit of the weight vector equals the eigenvector, right, q1, and this happens infinitely often with probability 1. That is, what we discussed was we have if you look at the trajectories of all these points, with probability 1 it enters a compact set, I mean it enters the basin of attraction, right, corresponding to this compact set of vectors here in the basin of attraction. So, this is what this means, and to satisfy condition 2 of the asymptotic stability theorem. So, what we had to do is we had to normalize, right. So, what we do here is we hard limit the entries of this weight vector, so that their magnitudes remain below a threshold, say A, right. The norm of w of n, which is equal to, I say, max over j absolute value of w j n, which is I look at all the components j and I take the maximum of the absolute value of the component of the vector and I limit that to A, right. This component is less than or equal to A, this is what I mean. Now, let A be a compact set of compact subset of Rm defined by the set of vectors whose norm is less than or equal to A. Sanger showed in 1989 that if this norm is less than or equal to A and this constant A is sufficiently large, then the norm of the weight vector at time n plus 1 is less than the norm of the weight vector at time n with probability 1. This is an important result. So, what this means is as iterations tend to infinity, that means I have large number of iterations, the weight vector Wn will eventually remain in this compact subset infinitely often with probability 1. Okay. And then the basin of attraction that includes all these bounded non-bounded vectors, and we say that this is BQ1 because that is the basin of attraction, that includes all vectors with norm bounded, and this implies that this compact subset A is part of that basin of attraction, right. And why this was important? Because unlike a linear dynamical system, we just have the eigen modes and then these are scalars and they are not time varying functions, they are just scalars, and you can just study the behavior of this linear dynamical system in an easy way. In the case of nonlinear dynamics it is not, because we have these points that are attractors, and then if you are tracing the trajectory of the weight vector, it will enter this basin of attraction and then land up at this attractor. And what is happening here is this basin of attraction around this eigenvector q1 includes all non-bounded vectors, and this implies that a compact subset of Rm is part of this basin of attraction, and that is what is happening here. Now, we can verify that rest all of the conditions in the asymptotic stability theorem are satisfied. That means Wn converges to Q1 with probability 1 and has lambda 1 as the associated eigenvalue. So, this is the take home message. So, now what it means is a single neuron with normalized Hebbian update aligns to the principal eigenvector of the correlation matrix, or in other words it adaptively extracts the principal eigenvector of the correlation matrix or principal component, because there is also the eigenvalue, there is also the eigenvector, and the weight vector converges to the eigenvector, and the eigenvalue is related to the variance sigma square, which is linked to the expected value of the square of the output. Okay. So, let me summarize these details. So, we started with stationary inputs, that means at every point of time the statistics of the data that you have is the same. It is a very important assumption, otherwise we would land up with correlation matrices that were time varying, and that analysis would be very hard. So, for stationary inputs Xn, a single neuron extracts the principal eigen component of the correlation matrix R, and I will leave this as a homework exercise. So, sigma square n as n goes to infinity heads to lambda 1, where sigma square n is basically the variance of the output yn, which is your output. Okay. And if you recall, output is basically linked with the input and the weight vector, right. It is the inner product between the weight vector and the data vector, right. Wn is a scalar, it is very important, and the expectation is over all realizations of the data vector, right, that is stochastic. Now, per Oyas update, which is essentially normalizing the Hebbian based rule, per Oyas update the Hebbian based filter converges to a fixed point with probability 1. So, these are the two cases. So, the lambda 1, which is the largest eigenvalue, corresponds to the limit of this variance sigma square n as n goes to infinity, and the eigen vector associated with lambda 1 is basically what the weight vector would be asymptotically, right. So, limit as n goes to infinity, your Wn, which is your weight vector, heads to your eigen vector, and that is the summary of the maximum eigen filter, which is Hebbian based maximum eigen filter. So, in short, what is the take home of this result? I have a single neuron and I do the most primitive update, which is this Hebbian based update, which works by correlations. So, I have a presynaptic input, which is my input data vector, and postsynaptic output is the output of the neuron, and I have a weight vector, which is a synaptic weight which couples the output with the neuron with the inputs, right. So, neuron is a nonlinear element here, and our rule for updation of these weights adaptively is according to Oyas rule, which is Hebbian rule normalized, and it was a simple rule, and the normalization led to a stable solution. And if we were to go deeper into the analysis as to why this normalized Hebbian rule works in practice and why it leads to a stable solution, we have to do stability analysis. And I think when we did the stability analysis, by expanding the normalization out using Taylor series and then simplifications, we landed up with a nonlinear difference equation, and from there we formulated this differential equation, because this difference equation and differential equation are related, assuming a sampling constant, right. And from there we began our journey trying to delve deeper into the eigenmodes of this nonlinear system, right. And then we looked into two cases, case 1 where you analyze the principal mode, and the other case where you look at all other modes that are not corresponding to k equals 1, and then we saw that all the other modes that are graded with respect to the largest eigenvalue, those modes dive to 0 and you just get the dominant mode, and that dominant mode is again governed by nonlinear dynamics, and we analyzed that dynamics and concluded that it is indeed a stable solution, or it is a stable attractor, right. So, therefore, adaptively when you compute your weight vectors, that asymptotically heads to the principal eigenvector of the data correlation matrix, and lambda 1, which is the eigenvalue, happens to be the variance of the output of the neuron. Okay. So, with this we conclude this study. So, if you have done principal component analysis or the KL transform in any machine learning course, or even as part of a signal processing course when you study KL transforms, all the analysis there is essentially based on linear transforms. So, in this case we have looked into nonlinear versions of this transformation, and we also looked at the kernel PCA, and that completes kernel based PCA methods and also this Hebbian based maximum eigenfilter.